In this video, we will be simplifying complex fractions, and we will use the least common multiple and multiply it to the numerator and denominator of the complex fraction to simplify. Let's first talk about what we already know about complex fractions. Any fraction can be written with parentheses around the entire numerator and entire denominator, and this fraction bar means divide. So any complex fraction can be rewritten as a division problem. Knowing this, we don't really need to know other steps to simplify complex fractions if we already know how to add, subtract, multiply, divide. Let's still go through those steps with this example. This x, which is not currently in a fraction, can be written as a fraction like any other whole number over 1. Now these two denominators, 1 and x, the common denominator will be x. This x over 1, we need to multiply x to top and bottom, gives us x squared over x. The 3 over x needs no change. Now at this point we would say keep the denominator the same and combine like terms in the numerator. And we don't have like terms, so it will be x squared plus 3. This addition, 1, we know is 1 over 1. But if we start with a whole number 1, the quicker way to get to those common denominators is to remember that 1 whole is any fraction where numerator and denominator are the same. Okay? So seeing this x squared here, I'm thinking, well, I need another x squared. Why not just make that 1 into x squared over x squared? And now 2 plus x squared. Same deal. Now, about that 1, I could definitely do it the same way, make it 1 over 1, but I think we can take advantage of a not too crazy quick way. When we see whole number 1, just make it same numerator, denominator. And the same situation as here, where we keep it x squared. In the numerator, we do not have like terms, x squared plus 2. At this point, we work in the fact that we have a division. The first fraction, x squared plus 3 over x. The second fraction, we know with division, we flip and multiply. This is x squared over x squared plus 2. And for the multiplication problem, we look, can we factor, then cancel? Well, the factor, this x squared we know is x times x. And we can use one of those x's to cancel this x. But it looks like these two binomials cannot be factored. We don't have a difference of squares, and we definitely don't have two squares at all. We're ready to put together our final answer. We have x times this x squared plus 3 in the numerator. In the denominator, x squared plus 2. And that's a final answer. Now going back to this original complex fraction, the clues that tell us that using the LCM is going to be a quicker way are that we see some whole numbers, basically, not fractions. We'd have a couple of fractions, but we have this x, we have this 1, so the fact that not every term in the complex fraction is itself a fraction means perhaps the LCM is a quicker way. What's also a great clue is looking at these smaller denominators, x there and x squared down here. If these denominators, if all the denominators of the little fractions, if they are similar to one another, then LCM is a good strategy to use. And we'll see how it works on this problem, and then we'll rip through a few more examples. In this method where we use the LCM, we're interested in the LCM of the small denominators. Any place where we have a smaller fraction in this complex fraction, we need to find the denominator. And the LCM we're using is the LCM of all of these smaller denominators. So here's an x to the first, there's x squared. LCM will need to use every factor we see, but the most times, so we're going with x squared. And now this x squared is multiplied to every term in this complex fraction. It follows the same rules that we can keep fractions equivalent if we multiply numerator and denominator by the same thing, because that's a fraction that equals 1. And also knowing that numerator and denominator of fractions are always contained in parentheses, we can see that this would have to be a distribute. So either think distribute because we're multiplying to a set of parentheses, or just always remember we multiply this LCM to every term in the fraction. Now when it comes to these smaller fractions, we are interested in seeing the denominators get canceled. And where we don't have fractions, we're just going to go ahead and multiply. Let me rewrite the multiplications we're going to do. I've rewritten this fraction, and now one by one we'll look at these multiplications. First, x squared times 1 more x, I'll start writing my answer down low, is x to the third. X squared times 3 over x. Now remember, we're thinking about canceling that denominator, and you can definitely, if it's helpful, think of our x squared as x squared over 1. This x squared we know is 2 x's available, and we'll use 1 to cancel that x down there. It will leave us with 3x over 1, and we'll pretty quickly just lose that 1 and use 3x. And we're using that 3x as the second term in the numerator of our answer. Okay, distribute to the x gave us x cubed. Distribute to 3 over x, we saw one of those x's from the x squared cancel our denominator, and the other one showing up in the numerator of our answer. Let's distribute in this denominator. X squared times 1, that's x squared. X squared times 2 over x squared. Hopefully we can see that the x squared will cancel with this x squared in the denominator. Leaves us with 2 over 1 is 2. At this point, we will not automatically be finished. We need to think, finally, can we simplify this fraction that we see? We should definitely not see any smaller fractions. If we still have some smaller fractions at this point in the problem, it means we did not do some work accurately up here. At this point, we should see only one big fraction bar. But can we simplify this fraction? We think, can we factor, and then can we cancel? In the numerator, I do see that we have a GCF. There's an x we can take from each factor. X out in front of parentheses and left inside x squared plus 3. In the denominator, definitely not difference of squares. In fact, we don't even have two squares at all. The x squared, but plus 2 is not leading us to anything we can cancel there. We'll just bring over x squared plus 2. We could factor the numerator only, and we cannot cancel any of these factors, so we have our final answer. It perhaps requires not as many operations as that first example, but it does require us getting a little bit of practice on this new technique. So let's do a couple more examples. Looking at this complex fraction, we have some terms that are fractions and other terms that are not fractions. Additionally, looking at our two smaller denominators, we see that they are both x plus 1. So this is a good candidate for simplifying by multiplying by the LCM. Since the two denominators that we see are both x plus 1, it means that we will be multiplying numerator and denominator by x plus 1. Now we need to be a bit more cautious with our multiplying because now we are multiplying by two terms, x plus 1. My preference is to rewrite this complex fraction with x plus 1 multiplied by each of these four terms. Here's our beginning fraction just rewritten with the four terms spaced out. And now I've multiplied x plus 1 to each of these four terms. Where I had a fraction, I've written x plus 1 over 1, just because it's sometimes helpful to very clearly see our numerator and denominator and what we can cancel. And where we didn't have fractions, I just have x plus 1 in parentheses. And you see I now have some extra sets of parentheses here. And my approach is that you can't go wrong having too many parentheses. You can make a mistake by not having parentheses. So what I like to do with these complex fractions is when I multiply by x plus 1, it is always in parentheses. When I'm multiplying by two or more terms, keep them in parentheses. Now it's also important for us to keep clear these four locations that we have coming from the four terms that we began this complex fraction with. Two terms up in the numerator, two terms up in the denominator. So one by one, we'll do the multiplying and the canceling from each of these four locations. Again, it's a type of problem where organization is key. And just notice that each of these four blobs contains one of our starting fractions and then the x plus 1, the LCM that we are going to be multiplying. The two terms from the numerator and these two terms from the denominator. Each of these four multiplied by x plus 1. Remember, where we have the fractions, we are looking for how does our denominator get canceled. The x plus 1's cancel. It leaves us with x over 1, which we know is just x. Be cautious here. This negative 2 does mean we will have to distribute negative 2. So this becomes negative 2x minus 2. Now what's going to happen here? We will combine terms. I'm going to save that for my next step. I'm still trying to just keep myself organized with these 4 different spots where I am multiplying and canceling. In the denominator, the x plus 1's will cancel. That leaves us with 3 over 1 is 3. In this last spot, we are distributing a positive 1. That becomes a positive 1x and plus 1. Now for sure, we are going to combine like terms in the numerator. We have x with negative 2x will leave us with negative x and minus 2. In the denominator, we have 3 can be combined with this positive 1, and then this term 1x. So that gives us x plus 4. Our last thoughts are, can we simplify this fraction? Can we factor, then cancel? Well, you might be able to see that there isn't any factoring that will lead to any canceling. So this is a perfect answer. If you did look at the numerator and spot that we have these 2 negative terms, which is often a clue that we should be factoring out a negative or a negative 1 as a GCF, that's a great move. That will put our negative sign out front. We're making now these 2 terms both positive, x and 2. So this is another fine looking answer. A negative x plus 2 over x plus 4. But either of these answers, I'd say, is 100% correct. Let's take this problem for our next example. It starts with finding all of our small denominators, the LCM that we are going to multiply to all of the terms that we have in this complex fraction. It will be the LCM of each of the smaller denominators that we see. Think back to what are our steps for finding the LCM, or the least common multiple. First, we need to make sure that everything is factored. We've got an x plus 2 and an x minus 2 that we cannot factor further, but this x squared minus 4 should be factored before we go any further with this problem. It's a difference of squares, and I've squeezed in there x plus 2 times x minus 2, the factored form of x squared minus 4. Remember, it's never a bad idea to rewrite if you find yourself getting squeezed together. It's just unfortunate to make a mistake because you're trying to work in too small of a space, and I will definitely be doing some rewriting soon. Let's find this LCM that we want to multiply to each of these terms in our complex fraction. Remember, building the LCM, we need to look at all the different factors that we see, and each one we need to use, and we need to use it the most times we see it in any single denominator. Let's look first at the x plus 2. We have it in the denominator here once. We have it up here once. So in our LCM, we only need it once. X minus 2, we have it here once, and up there once. Once is enough. Our LCM, x plus 2 times x minus 2. And we are going to have to, at each of these locations, multiply by x plus 2 and x minus 2. I'll definitely need to rewrite and give myself a little bit more space. Here's the original complex fraction. I have each of my 4 terms spaced out a little bit more, and I have kept my denominator, all of the denominators, factored. The ones that I couldn't factor, I have those enclosed in parentheses. The difference of squares, I definitely have those factors in parentheses. Now at each of these 4 spots, I'm going to multiply by x plus 2 times x minus 2, the LCM. And now I have x plus 2 times x minus 2 multiplied to each of our 4 terms. Where I didn't have a fraction, I just wrote x plus 2 times x minus 2. Where I did have fractions, I have that LCM in the numerator with 1 in the denominator. I do that just because it helps me be very clear about what I can cancel based on what I see in numerator and denominator. But if you are starting to understand that these factors that we multiply are always multiplied into the numerator, you might decide that you don't need to always put it as a fraction over 1. That's totally up to you. So now let's go through and look at what can we cancel, and the things that we cannot cancel, we will actually have to multiply. Let's start top left. There's nothing to cancel. We're going to have to multiply this all out. We know that x plus 2 times x minus 2 is x squared minus 4. That's our difference of squares. Now times 4 will take us to 4x squared minus 16. And that's what we get from this first term. Now let's carefully move to our next term in the numerator. We're glad to see lots of canceling. X plus 2's cancel, x minus 2's cancel. We're left with, always cautious with the sign, now we have a negative x over 1. That's just minus x. That's our numerator. In the denominator, in this location, the x plus 2's will cancel, but we cannot cancel anything else. We're left with 2 times x minus 2 in the numerator. We know the 1 in the denominator, we let that go, but careful here that we will actually have to distribute. It's a good thing about using all these parentheses is that it keeps us on track. It really shows us when we have to distribute, and it's very often. 2 times x is 2x. 2 times this negative 2, negative 4. And now our final position, x minus 2's cancel. We're left with a positive 2 times x plus 2. Again, distribute. Positive 2x plus 4. A quick check that at this time we don't see any more small fractions. That was our goal with the first part, multiply every term by LCM. We don't see any smaller fractions, so next it is combine like terms in the numerator and combine like terms in the denominator. In the numerator, we ended up with 3 unlike terms. I just wrote them in descending order, 4x squared minus x minus 16. In the denominator, 2x plus 2x gave us the 4x, and then negative 4 with the positive 4 equaled 0, canceled out. Remember, when we get to the end of the problem, my advice is that we always think factor and then cancel. Before I even try to think about what I could simplify in this problem, I should first think that I need to factor. Can I factor this trinomial up here in the numerator? And that answer turns out to be no. We cannot factor that trinomial 4x squared minus x minus 16. The 4x, you might be tempted to look at how it could work with each of these other terms, but since we could not factor in the numerator, it means we won't be able to do any canceling. The 4's that you see here should not be canceled. We would have to be able to divide the same thing out of every term that we see. So the 4's, because we don't have a 4 in this middle term, we cannot start dividing things by 4. And if you just have the approach that I'm going to try to factor first, and if I cannot factor, I won't cancel, then we'll stay on the right path and end that problem right here. Here's our last example. You might want to pause the video and give this one a try on your own, just to see how you can do so far. Remember, our approach for now is that we are multiplying numerator and denominator by the LCM, and we are looking at each of our smaller denominators to determine what our LCM is. Now in this case we only have 3 terms. That's okay, we'll still take the same approach that we've been using so far. To find our LCM, we will first make sure that each denominator is factored. The x plus 3 is good, this x minus 3 is good. X squared minus 9, we can deal with that. That's a difference of squares. We can factor as x plus 3 times x minus 3. Next, let's build this LCM. We need to use x plus 3, but it looks like we only need 1. And the same goes for x minus 3. We only need 1. Now I'll rewrite this problem with a little bit more space so I can multiply each term by this LCM. Now let's go through and identify what factors we can cancel and what leftover factors we need to multiply together. In our first location, we have factors x plus 3 that we can cancel. Left over, we need to do x times x minus 3. We will have to distribute. That will take us to x squared minus 3x from that first spot. Next location, we have these factors x minus 3 that can cancel. Left over, negative 3 times x plus 3. We are distributing negative 3. That leaves us negative 3x minus 9. That takes care of our numerator. In the denominator, x plus 3's cancel and x minus 3's cancel. That leaves us with only 3. Next, let's combine these like terms. X squared minus 6x minus 9. It's all over 3. Finally, we're looking at this fraction. Can we factor and then cancel? Well, this trinomial, it looks a little bit tempting. Our steps for factoring this x squared minus 6x minus 9 would be, can we find a pair of numbers that multiplied together would equal this negative 9, added together would equal that negative 6, and I don't think that we will be able to find this pair of numbers. It does not exist. Now, if you're thinking about, well, this looks like a problem where we used to have to do some dividing, like splitting these terms up into 3 separate fractions. You could do that. It would not be wrong, but typically my advice is, when we get to the end of the problem, just think factor and then cancel. And after those two thoughts, we're okay to just leave it as is. Because we could not factor that numerator, and there's no factoring to do with this denominator, then we just end it. I like this as my final answer for this simplified complex fraction.